Hey everyone, my name is Valentine. I am your host here at Codex Hive Labs. We've been looking to document more of our process and findings, and I think we have a really special one for you today, as this podcast is directly inspired by my recent research on the universal constant of lambda is approximately equal to E. Euler's number.
There's a number in physics that keeps showing up where it technically shouldn't. It's not pi, and it's not the speed of light. It's E, Euler's number. 2.718, the number you learned in high school for calculating compound interest or population growth. We usually think of it as a tool for statistics or finance, not necessarily the bedrock of space-time. But what if that's wrong? What if E isn't just about growth, but about scale? Today we're looking at a set of research that proposes something radically different about the architecture of our universe. It's called the Unified Fractal Field Theory, or UFFT. And if the papers we're diving into today are correct, we might have to rethink everything, from how galaxies spin to how earthquakes release energy. The central thesis here is that space-time isn't the smooth, continuous sheet Einstein pictured. Instead, it's fractal. It repeats, and it scales. We're going to walk through 9 specific publications that lay out this framework, covering everything from the dark matter problem to fusion reactors. And the claim at the center of it all is that the universe has a preferred scaling factor, and that factor is E. Part 1. The Fractal Fabric. So let's start with the problem UFT is trying to solve. For 100 years, physics has been divorced. We have general relativity over here, handling gravity and big heavy things like stars and black holes. And we have quantum mechanics over there, handling the tiny jittery world of atoms. They don't speak the same language. Relativity is smooth, quantum mechanics is chunky or discrete. The first paper in our stack, simply titled Unified Fractal Field Theory, proposes a bridge. The author suggests that the geometry of space-time possesses a recursive structure. That means the laws of physics don't just apply at a scale, they repeat across scales. This is what we call scale invariance. Now, usually when we talk about fractals, we think of those psychedelic computer-generated images, the Mandelbrot set. You zoom in and you see the same shape again. But UFT argues this is physical. It posits that energy and mass organize themselves into patterns that repeat at logarithmic intervals. And this is where that number comes in. The theory identifies a specific scaling constant, lambda, which it equates to Euler's number, E. But it gets weirder when you look at time. The second paper, the Fractal Time Framework, or FTF, argues that time itself isn't a smooth river. It's discrete. It flows in a log-periodic rhythm. The paper introduces a transformation equation where time scales according to a ratio R, which is approximately 1.587. The text describes this as a golden ratio variant. So imagine a clock that doesn't tick-tock linearly, 1, 2, 3, but instead ticks in a way that compresses and expands based on a logarithmic scale. The theory suggests that what looks like chaos to us, whether it's the unpredictable nature of an earthquake or the turbulence in a plasma reactor, is actually just us failing to see this hidden log-periodic clock. We're measuring with a linear ruler in a fractal world. This leads us to the lambda A hypothesis, the third major paper. This is the glue. It argues that this scaling isn't arbitrary. The constant E emerges naturally from the recursive dynamics of space-time itself. It's suggesting that E is the equilibrium point, the stationary point where the expansion of space and the flow of time balance out. It connects the spatial scaling of UFT with the temporal scaling of FTF. Essentially, if space scales by E, time scales by this golden ratio variant, and they lock together to form the stable reality we see.
Part 2. The evidence in the stars. Okay, that's the theory. It's elegant math. But physics requires evidence. And usually when you introduce a theory of everything, the first place you look is the heavens, specifically galaxies. One of the biggest headaches in modern astrophysics is dark matter. We look at a galaxy like the ones in the Spark database. That's the Spitzer Photometry and Accurate Rotation Curves catalog. And we see stars moving too fast. Newtonian gravity says they should fly apart. So we assume there's a halo of invisible, dark matter holding them in. But we've never found the particle. The fourth paper, Lambda E Hypothesis, Universal Scaling in Spark Galaxies, takes a different approach. It analyzes 165 galaxies and finds a universal scaling relation in their rotation curves. But here's the kicker. It doesn't need a new particle. It models the dark matter effect as a geometric consequence of this fractal scaling. It argues that the gravitational field itself scales logarithmically. If you applied the lambda E scaling factor, the missing mass just appears as a property of the field. The rotation curves fit the data not because there's invisible sludge out there, but because gravity behaves differently at those massive scales. Specifically, it behaves according to this fractal law. It suggests that what we call dark matter is actually just the shadow of this higher dimensional fractal geometry. It's a bold claim because it challenges the standard model of cosmology. But the paper points to a specific convergence in the data, a drift toward that lambda value of 2.718 across diverse galactic systems. It's saying, look, the math works without the ghost particles.
Part 3, Shaking the Foundations. Now let's bring it down to Earth, literally, because while galaxies are huge and slow, earthquakes are sudden and violent, and predicting them is notoriously impossible. Seismologists usually rely on Omori's law, which describes how aftershocks decay over time. It's a power law, and it's decent, but it's not perfect. Papers 5 and 6 on our list focus on the Ridgecrest seismic event. This was a major earthquake sequence in California in 2019. The author applied the fractal time framework to the aftershock data. Remember that log periodic clock we talked about? They looked for those hidden rhythms in the aftershocks. The results reported are frankly staggering. The paper claims an improvement in aftershock prediction significance of 87.8 sigma. I need to pause on that number. In particle physics, like at CERN, a 5 sigma result is considered a discovery. That means there's a 1 in 3.5 million chance the result is a fluke. 87.8 sigma it's astronomical. It implies a statistical certainty that is effectively absolute. The paper, FTF Validation, details how this was achieved. By treating the aftershock sequence not as a linear decay, but as a log periodic oscillation, the model predicted when the energy would release with incredibly high fidelity. It suggests that the Earth's crust doesn't just crack randomly, it cracks according to a fractal schedule. The stress accumulates and releases in waves that follow that same lambda E scaling factor. This leads to the development of the specific tool mentioned in paper 7, the log scaling flow metric, or LSFM. This is the mathematical engine under the hood. LSFM measures the deviation of a system from that universal fixed point. It's a way of quantifying how fractally aligned a system is. In the case of Ridgecrest, the seismic data converged tightly around that lambda scaling factor. This is arguably the most practical application of the theory so far. If you can predict aftershocks with that level of precision, you're not just doing theoretical physics, you're saving lives.
Part 4. From Fusion to the Cloud. The beauty of a unified field theory is that it should apply everywhere. If it works for galaxies and earthquakes, it should work for everything in between. The final papers in our list test this hypothesis in 2 very different man-made systems: AI data centers and nuclear fusion reactors. Let's look at paper 9. Log scaling flow metric analysis of regime transitions in HL3 tokamak. The HL3 is a fusion reactor, a donut-shaped machine that uses magnetic fields to contain superheated plasma. The goal is to create clean energy, but the problem is disruptions. The plasma is unstable. It wants to crash into the walls. predicting these crashes is the holy grail of fusion research. The paper applies the LSFM to the plasma data. It treats the turbulence in the plasma just like the aftershocks of an earthquake. And again, it finds that the regime transitions, the moments the plasma goes from stable to chaotic, follow that log scaling law. It allows for disruption prediction by spotting the fractal signature of a crash before it happens. Then, looking at paper 8, we pivot to AI data center validation. Modern AI workloads are bursty. They spike and drop in complex patterns. The author analyzed workload traces and found that same lambda approximately E temporal scaling. The flow of information in a server farm apparently follows the same fractal dynamics as the flow of plasma in a reactor or the rotation of stars in a galaxy. This implies that turbulence, whether it's gravitational, seismic, electromagnetic, or informational, is all the same phenomenon at the structural level. It's all governed by UFFT.
So, what are we looking at here? We have a framework that starts with a pure mathematical hypothesis about fractal spacetime and the number E. It moves to the cosmos to explain dark matter. It drops down to geology to predict earthquakes with unprecedented statistical strength, and then it slides into engineering to stabilize fusion reactors and optimize data flows. The common thread is the log scaling flow metric. It suggests that we've been missing a coordinate. We measure x, y, z, and t, but we ignored scale. We ignored the fact that the ruler changes size depending on where you are in the fractal hierarchy. If these papers hold up, specifically that 87.8 sigma claim for Ridgecrest, we aren't just looking at a new theory. We're looking at a new toolkit for predicting the behavior of chaotic systems. It turns the unpredictable into the inevitable simply by changing the clock we use to measure it. It's a lot to take in, but next time you see the number 2.718, don't just think about your savings account. Think about the structure of the universe. That's it for this deep dive into the unified fractal field theory. If you found this fascinating, pass this episode along to a friend who loves physics or anyone who appreciates a good challenge to the status quo.